Good afternoon, everyone. We are very pleased to welcome you and thank you for participating in the first cycle of virtual seminar of our program. First, I would like to reinforce the importance of the Human Resource Program of the National Petroleum Agency for the innovation process and knowledge dissemination. The National Agency of Petroleum, Natural Gas and Biofuels is the regulatory body for activities in the integrated oil, natural gas, and biofuels industries in Brazil. It's linked of the Ministry of Mines and Energy. Currently, we have 55 programs in Brazil. Compose our program professors, research, and students from several undergraduate courses. Besides that, students from three graduate courses, civil engineering, geoscience, and nuclear and energetic technologies. For today, we have the privilege of having as speaker the Master of Science and Environmental Engineering and Science, Paola Barreto Quintero, that will present the webinar entitled Pilot Test for In-situ and Ex-situ Aerobic Bioremediation of a complex mixture of contaminants at a NAPL-impacted site in Brazil. On behalf of our program, we really appreciate you giving this talk. We also take the opportunity to thank the moderators, our special guest, the PhD Erin Mack, specialist in bioremediation from Dupont, and Professor Sávia Gavazza, member of our program. To continue, I invite our visit research Alan Almeida to give some information about the webinar and make a brief presentation. The speaker, Paola Quintero, and the moderator, Erin Mack. Thank you.
Okay, thank you, Professor Antonino. Good afternoon, everyone. I'd like to thank again Research Paola for accepting the invitation to give this e-talk. I also thank all chairs for the opportunity to have them participating in this e-talk, as well as everyone who is following us live on Facebook and also on a YouTube channel. I also ask viewers to subscribe to our channel and like this video so that you can have access to new webinars in this field for us to share information about our program. Now talking a little about our speaker's CV, Paola is a Colombian chemical and environmental engineer with a master's degree from Clemson University in the United States. Paola has 10 years of experience. She worked supporting remediation projects for Dupont Corporate Remediation Group throughout Latin America and now works for Jacobs Engineers. Out of the Philadelphia office, supporting projects in Latin America and the United States. Paola's experience is most focused in design, planning, and performance evaluation of bioremediation solutions for contaminated sites. Paola also experienced in development and refinement of site conception models, and has also supported due diligence evaluation for divestiture acquisition of sites. Now the Erin's Mack CVs. Dr. Erin Mack is a principal technical consultant in the Curitiba Corporate Remediation Group. She started with DuPont in 1999 as a subject matter expert in environmental microbiology, biodegradation, and mercury fate and transport. She currently serves as a technical research and manages external research programs in these areas for Curitiba Agri-Science. Dr. Mack has applied results from these external programs to design remedial strategies for mercury, chlorinated solvents, and nitroaromatic compounds in the field. She holds a Bachelor's of Science in Biology from University of Puget Sound, a Master's of Arts in Microbiology from Southern Illinois University of Carbondale, and a Doctor of Philosophy in Microbiology from the University of California at Davis. After graduating from the University of California, she was National Research Council Fellow at the United States Environment Protection Agency Laboratory in Athens, Greece. Well, it's worth to mention this lecture is going to be very important for our program, including faculty, grad, and undergrad students. We currently have 5 students working in the field of environmental biotechnology. Then have been working in bioremediation of petroleum residues. Therefore, we hope that the webinar will give them more knowledge about the topic. Now, before Paola begins, I'd like to remind that questions will be asked in the end of the lecture by chairs, followed by social media audience. I also remind listeners that everyone can ask questions anytime on chat, and they will be answered after chair's questions in the end of the lecture. We also have our attendance list on the chat, just for undergrad and grad students from our program. Finally, I'd like to call researcher Paola to give her presentation. Please go ahead.
Thank you very much, Alan, for the introduction. So let's make sure that you all are seeing my screen, and let me just swap them here really quick. So hopefully this is coming through for you guys now. Can you see my screen?
Yeah, we can see. Thank you.
Sorry, Alan, can you see my screen?
Yeah, we can see. I can see.
Alan, can you hear me?
Yeah.
Okay, can you see my screen?
Yeah, I can see.
Okay, perfect. Yeah, sorry, I couldn't hear you. Okay, well, thank you very much, everybody, for connecting here to this webinar. It's a pleasure to be here with you today. I would just like to add that, if you feel more comfortable asking questions in Portuguese or Spanish, I'm a Spanish speaker and I speak some Portuñol, but it's not great. So I really didn't want to mess up with the beautiful Portuguese language. So I figured I would just go in English. So anyway, yeah, feel free at the end of the presentation to ask questions in whatever language you feel more comfortable with. So I am here today to discuss with you and share our experience developing a pilot test program for in-situ and ex-situ aerobic bioremediation of a complex mixture of contaminants. And as Alan mentioned, this is a NAPL-impacted site. NAPL stands for non-aqueous phase product or non-aqueous phase liquids. So this site is highly contaminated and it is located in Brazil. We have been working in this project for around 10 years, well, 8 years actually, and are finally closing in into the remediation stage. So what we are going to share with you is some of the preliminary results we have gotten from these bio pilots, and these tests are still ongoing, and we'll get more data as time goes by for the next 6 months. But in the meantime, we just wanted to share with you some preliminary and very exciting results that we are obtaining. So let's move on. So before actually jumping into the content of the presentation, I would like to acknowledge that this is everything that you will see here is the product of many months of work by a larger team. And you can see here some of the team members. First, Quintero, who owns the site and has sponsored all this great work that we are doing together. At Vision, who is doing most of or all of the field efforts, implementing the pilots and conducting sampling and supporting data evaluation. Also, University of Toronto, who has conducted significant amount of research and microcosm studies to help us evaluate the biodegradability of some of the contaminants we have at this site. we have a very exotic mixture of contaminants. You'll see that in the next few slides. So because of that, like Corteva had to sponsor a lot of research programs to help understand if these contaminants could be treated by biological means. So we had University of Toronto supporting those efforts. Clemson University also supported these efforts. University Federal of Pernambuco with Professor Sávia has also been doing a significant amount of work that is still ongoing. We have University of West Florida, and we also have Geosyntec consultants supporting a very innovative evaluation approach for the performance of these pilots. It's basically focused on compound specific isotope analysis. We won't get into the details of that in this presentation. We just wanted to acknowledge their participation as well. And then Jacobs as well, who has been leading the design activities and data evaluation for this pilot program. So again, everything you'll see here is the product of collaboration. I think actually I want that to be one of the key messages from this talk, and we'll see how that works out in the next few slides. So our agenda for today, we are going to cover 6 topics. So first, we'll start by describing what is our challenge, what's the problem we are trying to solve. Then we will go through a quick summary of microcosm studies that were performed in advance of this pilot test program to help evaluate if bioremediation technologies could be effective treating the contaminants we had at this site. Then we'll go and review quickly the pilot test conceptual design. And again, we are talking about 2 pilot tests. We have a engineer wetlands pilot test, and we also have a biosparging pilot test. So we'll go quickly over like the basis for design of these 2 pilots, and then we'll advance and review implementation and results obtained to date for each one of those 2 pilots, and then we'll close in with next steps and a final message at the end. So advancing with our agenda, let's just start first with our challenge. What is this site, and why are we doing like all this work? So as we mentioned earlier, the site is located in Brazil. It's actually in northeastern Brazil, so not that far away from all of you in Pernambuco. It's in the state of Bahia, actually. It's in the largest petrochemical complex in the southern hemisphere. Here you can see an aerial picture of the site. Here, like we mark the site boundaries, and then you can see in shaded blue, I'm trying to highlight there most of the former production units where the most or the bulk of the contamination is currently present on site. So most of our remedial efforts are focused in cleanup of contamination in these areas. We have contamination in soil and groundwater, but the pilot tests that we'll be discussing here are aimed at treating dissolved phase contamination. So that is contaminants present in groundwater. So let's travel quickly on time and let's see how this problem originated. These are some historical pictures from the site almost 40 years ago. Well, yeah, 30 years ago, actually. So when the site started operations, there wasn't any hazardous waste processing facility in the area. So what ended up happening is that previous owners at the beginning of the site operation didn't have any means to dispose or treat all the hazardous waste that generated from site operation. So over time, they just started storing these waste from production processes in an area at the site, and then throughout several areas at the site in metallic drums. These metallic drums were corroded, and then over time they spilled their contents into the soil. And you can see here, some of like the pool of contaminants that we had like above ground. The site doesn't look like this anymore. The site has a very long and complex history of ownership. Actually, the originators of these impacts do not correspond to the current owners. So anyway, what you're seeing here doesn't exist anymore, as you see here. All of these drums have been cleared up, but again, these impacts generated by the release of these products into soil and groundwater has remained, and we have been working actively for the past 8 years with site owners, and I know they have decades of actually working in the cleanup of this site. But the mixture of contaminants that we are dealing with here from all the history of operation at this facility is very exotic. We mostly have chlorobenzenes, chloronitrobenzenes, and chloroanilines. This type of mixture is not very easy to find. There are not many industrial facilities with this type of contamination. So that's the reason why Corteva had to invest a lot in developing a robust research and development program to assess the potential of biodegradation for the contaminants we had here. So moving on here, the site shut down operations in 2014. So the site is not actively producing any products right now. It used to be an agrochemical production facility, but since it has been shut down, all the efforts are currently focused on demolition and removal of former production units, and then the remediation and cleanup of soil and groundwater that have been contaminated historically. So in this picture, you can see trying to illustrate or make an analogy with an iceberg for the situation that we have here. So on the tip of the iceberg, what we can see in the surface is all these former production units and all production buildings at the facility that some of them haven't been used in decades, but actually still have chemical products in them. Well, the site is now actively working in removing and demolishing all these former units. But at the same time, again, that's the tip of the iceberg. That's what we can see. At the same time, we have a large history of impacts to the environment, mainly soil and groundwater. And you can see here some pictures of the subsurface. If we do some digging, some trenching, or install some wells, some areas are very impacted with non-aqueous phase product, which we call NAPL. And that's what you can see here, some of the liquids that are surfacing or accumulate, or even these orange coloration soils that we have in some areas. So again, that's what we are trying to remediate, these contaminated soils and contaminated groundwater. But again, the focus of the pilots that we'll discuss here is on groundwater remediation. For the soil remediation program, we actually have another set of remedies that are being evaluated right now. So that's our challenge, but of course, from challenges come many opportunities. So here's a picture of two key team members that are on site. Here is Ligia Carvalho. She works at the laboratory at the site, and she has helped us conduct treatability studies, both based on bioremediation and other technologies, and she is leading all the analytical efforts for sampling sample analysis at the site. And then we have Rui Silva here, who has been leading on Corteva's behalf all the field efforts and implementation. So they have been actually two key team members to help us deliver what you will see today. But anyway, again, we have a big challenge here, but this challenge is actually an opportunity to do something innovative, something different in Brazil. But most importantly, we also wanted to do it sustainably. So earlier in the development process, we developed sustainability goals for the remediation of this site. So we wanted to treat all this contamination, but we also wanted to do it in an efficient, sustainable manner. And along those lines, we developed sustainability goals associated to energy usage, water usage, taking advantage of local flora and fauna in the area. So aligned with all these sustainability goals that I'm not listing here just for the sake of time, but Corteva decided to focus all the remediation efforts for contaminants in groundwater on bioremediation technologies. We wanted to let the microbes, we wanted to let nature do the job. We just wanted to help it. Like, what is missing for nature to help us drive this work? Is it missing oxygen? Is it missing nutrients? Or maybe we don't have the right microorganisms to do this. Do we need to add them? So all the focus has been driven by those goals, and that's what we'll be sharing here in the next slides. So as I mentioned, now in this next section, we will discuss briefly the microcosm studies that were conducted. So we have a very exotic mixture of contaminants that is not typically seen in other sites. So we had to do some research and understand if some of these contaminants could be degraded at the facility. First, if they could be biodegradable, because some of the contaminants we didn't even know if they could be biodegradable. They hadn't been reported or studied in the literature. So dichloronitrobenzenes, for example, those are contaminants that they didn't have any previous reports in the literature of being biodegradable. So University of West Florida focused their work in developing microcosm studies to understand if there are microorganisms on site and also in general that could degrade these contaminants, and we did find them. But here I'm just sharing one slide from University of Toronto, where we are displaying some of the results obtained for microcosm studies evaluating the potential for degradation of chloroanilines, which were important contaminants at the site. So you can see, like, the main chloroanilines we are listing here are 2-chloroaniline, and then 2,3-dichloroaniline, and 2,5-dichloroaniline. We actually have also 3,4-dichloroaniline being like a key compound of concern. But what you can see from this plot is that after receiving soil and groundwater samples from the facility, University of Toronto assembled these microcosms. They had like a set of aerobic microcosms, a set of anaerobic microcosms, and the contaminants of interest were spiked into those bottles. And then you can see that we had like rapid degradation. Well, not that rapid, I guess. Over the course of several weeks, we are seeing these contaminants going away. And again, here I'm only focusing on showing the results for chloroanilines. But just like University of Toronto did this work, University of West Florida, for example, focused on understanding biodegradation of dichloronitrobenzenes. Clemson University looked at degradation of chlorobenzenes. And anyway, different parties have been focusing in different pieces of the work. So I'm going to summarize all this work in this slide. So Corteva sponsor this very comprehensive treatability or study or microcosm studies. And then here you can see a list of the main contaminants that we have on site and that we need to clean up, we need to remediate. And then you can see also each one of the universities that collaborated with these microcosm studies efforts, and then for each one of the pathways that were assessed, either aerobic or anaerobic biodegradation, you can see whether this contaminant was studied or not. If it was studied, then you will see a check mark or a cross if we had successful biodegradation of that contaminant or not. So across the different studies performed, you can see that most of the contaminants were biodegradable. So that meant that based on the site samples that we obtained, we had the right microorganisms already naturally present inside materials. And whenever we just gave them oxygen, they would like mineralize these contaminants. University of Toronto also did some anaerobic work. However, we didn't choose to go down that path because anaerobic processes generate intermediate compounds that are not a better endpoint for remediation. So they are, some of those endpoints or middle points are as toxic as the parent contaminants. So that's why we decided to go down the aerobic path, focusing on contaminant mineralization. That is, the contaminant is destroyed, is oxidized to carbon dioxide and water. So going ahead, like once these pilot tests or these microcosm studies were completed, and once we understood that aerobic processes were the right path to pursue, we started narrowing down the list of remediation technologies to those focused on aerobic biodegradation of contaminants. So we then decided to, the team worked together and decided to develop a biosparging pilot test. And here you can see a representation of the pilot test that we are implementing at the site. So the main objective of this pilot test is to increase the aquifer contaminant mineralization capacity by providing oxygen. So from the microcosm studies, we knew we had the microorganisms, or most of the right microorganisms, already naturally present in there. They are just lacking the right conditions to degrade those contaminants for us. So how can we facilitate that process? How can we give these microorganisms what they need to do this work? Well, we can sparge air in the aquifer, and that will serve as a source of oxygen for contaminant, to support contaminant mineralization. So here is like a conceptual sketch of the pilot test we have. So we have 2 biosparging wells, and that's where we inject air. We are injecting air. We are not injecting pure oxygen. Those systems are a little bit more complex and more expensive. So we started first just injecting air. We also have a series of monitoring wells, which you see here in green, which help us collect samples over time and measure contaminant, measure technology performance. We also have salt vapor extraction wells, and that was to provide a means for vapor capture. Like, so all this air that we are sparging into the aquifer, if it happens to go to the vadose zone or the unsaturated zone, we don't want that releasing into the outdoor environment. We want to capture any vapors generated from our remediation activities to prevent any concerns associated to that. So we have a salt vapor extraction system covering the unsaturated zone. And then we also had venting wells in the aquifer to provide means for or to prevent stratigraphic air trapping. So any air that accumulates in the subsurface underneath any low permeability layers, we can provide a pathway for this air to escape. So that's basically the layout of our biosparging pilot. Then if we go to the next slide, we see that we are also trying to enhance this pilot with groundwater recirculation, which is another technology. So besides sparging air, we are also extracting, or like a second stage of the pilot consists of extracting water from the aquifer, oxygenated above ground, and then add any amendments. In this case, we are considering pH adjustment because pH in the subsurface is decreasing, and that may stop degradation. So we want to ensure those conditions stay right, and we think the groundwater recirculation is a technology that will help us look into this. And then this technology also offers an option for remedial implementation in areas that are not as accessible because they have buildings still in place that have not been demolished. So here is like the second stage of the conceptual design for the biosparging and groundwater recirculation pilot test. Here you can see a layout of the pilot test area. So I'm going to go quickly through this. We have sparging wells, we have monitoring wells to collect samples, and they are distributed in different stratigraphic units. So we can have like a vertical understanding of performance of this technology. We have other set of monitoring wells in another stratigraphic unit. We also have venting wells to prevent this stratigraphic air trapping. We have multi-purpose wells that are used for venting and also for groundwater extraction as part of that groundwater recirculation component. We have venting and groundwater injection wells. And then lastly, we have salt vapor extraction wells to prevent any vapor accumulation issues in the vadose zone, and then vacuum monitoring points to support that soil vapor extraction system. So that's basically the layout we have right now in the field for the biosparging system. For the wetland system, again, like, can we enhance biodegradation of these contaminants by providing a source of oxygen? Well, the site currently has a hydraulic barrier, so they are pumping contaminated groundwater from the aquifer, and then they are sending it for treatment to another third party. Well, can we take that water and treat it ourselves? So we started looking into constructed wetlands, and here's like an image depicting the different type of processes that help with contaminant treatment in wetlands. That includes sedimentation, biodegradation, phytoremediation, adsorption, and even volatilization. Some of these processes are processes that we don't want, but they do happen. However, what we are trying to stimulate mostly here is microorganisms to degrade these contaminants present in that water from the hydraulic barrier effluent. So here is a layout of the pilot test. So we are testing 3 treatment configurations. We have a head tank that basically is our reservoir of water that will be used for treatment. Then we have a neutralization or equalization tank. We have one set of treatments that are being pH adjusted, another set of treatments that are working at the background pH. And then after feeding the effluent into that equalization tank or neutralization tank, that effluent is distributed to upflow gravel beds, which you can see here. Hopefully you can see my pointer. Upflow gravel beds that are oxygenated. We are sparging air into them, and here we expect the bulk of biodegradation and treatment to occur. Some of these upflow gravel beds are unplanted, like these ones that you see here. Other treatments are planted. We want to understand what's the effect of plants in treatment of contaminants in this type of systems for the mixtures we have. And then you can see that these offload gravel beds in some of the configurations are followed by planted marshes. These marshes are more of a polishing step that will help us take contaminant concentrations to those very low levels that we want them to be at. So anyway, we had several hypotheses we wanted to test. We want to know if plants are necessary for or can help with contaminant treatment. We want to know how important is pH adjustment for treatment. We want to understand if a configuration in series or a configuration in parallel would work better or would yield better results. So that's why we are testing several arrangements of the system to get an answer to all those questions. So here is a picture of like the 3D drawing, I guess, for pilot test implementation. So again, we have 2 treatment trains, treatment train A, which is, you can see treatment train A1, A2, and A3. Each one of those configurations are aligned with that slide I just showed to you. And then treatment train A is the one that has pH adjusted. And then treatment train B, which is the one here in the other side of the screen, this one is exactly a reflection or a mirror of this other set of treatments. The only difference is that it doesn't have pH adjusted. So now let's just go through pilot test implementation and results that we have obtained to date. So here you can see some pictures of the biosparging pilot test area. The system started up operations in June last year, no, June this year, actually. So you can see here in the pictures, here in this container, you can see, well, it's where we have all the soil vapor extraction equipment. And then here in this other container, we have the biosparging equipment. So the blower that blows air, and then we have the injection points are actually here in the center of the area. And you can see like all these pipes connecting through. That's mostly for the groundwater recirculation component, where we intend to extract and then recirculate, upgrading groundwater to also help with treatment. So anyway, you can see the area is very busy. We have many monitoring wells throughout, but it's like very clean, very neat and organized. Actually, one of the best ones we have ever seen. So this is what the pilot test looks so far, but in terms of results, what have we achieved? So After 6 months of operation, and again, this pilot test is still ongoing. It will continue until June next year. So we are still getting more results. But in the meantime, this is what we have. So we have that contaminant concentrations have decreased several orders of magnitude. So that's like a big change since the starting point we had. We also have dissolved oxygen concentrations that have increased significantly. So that was the main objective of this pilot. We want to provide oxygen to the subsurface so microorganisms available in there can degrade contaminants. So we saw dissolved oxygen concentrations going up, and along with that increase of dissolved oxygen, we see these microorganisms kicking in and eating away these concentrations of contaminants that we have in the aquifer. Along with that contaminant mineralization process, we have also seen dissolved iron concentrations decrease, which is consistent with an aerobic environment. We also have nitrate concentrations increasing, again, consistent with that aerobic environment that we are enhancing. Besides that, nitrite is also a product of biodegradation from one of the set of contaminants that we have at the site. So we expect that nitrate to increase also as we remediate the aquifer. We also have seen pH decreasing, which is also consistent with the type of bioremediation processes that we expect to see. And then because we don't want that pH to go down further, we need to make sure that we provide means for pH buffering in the aquifer. So we will initiate that groundwater recirculation system that I was talking about to help adjust that pH and ensure that we have the best conditions possible for microorganisms to continue doing their work. We also have chloride concentrations that we expect that these chloride concentrations would increase, which would be consistent with the biodegradation or mineralization of the type of contaminants we have at this site. However, we haven't seen much of that chloride generation kicking yet. We are keeping a close eye on that. But anyway, here are like some graphics that will help depict some of these results. So here you can see the dissolved oxygen concentrations in the pilot test area before we started up operations. So as you can see, all dissolved oxygen concentrations were between 0 and 2 milligrams per liter. Actually, they were all below 1 milligram per liter. So very low dissolved oxygen concentrations. However, now that we started biosparging activities, you can see how dissolved oxygen concentrations have changed throughout the pilot test area. You can see that close to the sparging wells, which I am highlighting here in red, we have very high dissolved oxygen concentrations, are higher than 7 milligrams per liter, and then we still have really good oxygen distribution in areas that are further downgrading from the sparging wells. So we have achieved that objective of efficiently providing oxygen to the subsurface. Now, what are we getting in terms of analytical results? I told you that we were getting contaminant concentration reduction in the order of several orders of magnitude. So you can see here, like the starting concentrations that we have for this monitoring well, for example, it was around 10,000 milligrams per liter, and now we have around 10 micrograms per liter, I'm sorry, over the course of a few months. So some wells, most of the wells have responded very well. Most of the contaminants are being degraded. There are a few exceptions here and there. Like, for example, we are seeing some contaminant concentration increase for nitrochlorobenzenes in this well. That's something that we are looking at. We also expect that with this pilot test, we may be mobilizing some of this free product phase in the aquifer. So that's probably why we are seeing this increase, and probably these nitrochlorobenzene degraders in certain areas are not as active or may not even be present. We have found that these are rather tricky to stimulate and find and maintain. So here are the results again today. I'm not going to spend more time on it. Just going to jump quickly now to the wetland pilot test implementation and results. So here are some pictures of what the system looks like currently. Again, I mentioned to you earlier, we have 2 sets of treatment trains, and each treatment train consists of 3 configurations. So here you can see the upflow gravel beds, which are these cubes, white cubes that you see at the front. And then you can see the planted marshes, which are these blue circular features with very happy plants growing in them. You can see also that some of the upflow gravel beds are planted, some others are not planted, and actually others were originally planted, and then the species that we were testing are not as happy as we would like them to be. So we are going to be replacing some of those. But anyway, what have we obtained so far for the wetland pilot test in terms of results? So we have also that contaminant concentrations have decreased several orders of magnitude along the treatment train. And consistent with that trend, we also see chemical oxygen demand, which is a bulk measurement of presence of contaminant or organics in that effluent that we are treating. So that's chemical oxidation, chemical oxygen demand and COI concentrations go along hands, and they are consistent. We are also seeing an increase in chloride concentrations, which again we expect to generate from degradation processes. Nitrate and nitrite have not increased as we would expect that to occur. However, we need to take into account that there is a large population of microorganisms that is growing and will represent like a large demand for nutrient. So we expect that some of this nitrogen is being taken, is like being consumed by not only by plants but also by microorganisms. We haven't seen a significant difference in treatment effectiveness between the pH adjusted and non-pH adjusted treatments. So far, it looks like pH, it's not a critical variable here. So originally, we thought that the pH of this effluent was going to be very low. We have seen pH at this side of around 4. But however, for this pilot test, the effluent that we are receiving, the pH is already close to 7. So it's very close to ideal conditions. So even though we have been adjusting pH, it hasn't been a key variable so far. So we are seeing very similar results between the two treatment trains. And then again, as I mentioned earlier, most plants have adapted to the system conditions and are growing strong and healthy, with a couple of exceptions that we are actually working on understanding what's happening there. So here are only a couple of slides displaying the results that we have obtained. So you can see for treatment train A, we have 3 configurations. So configuration 1, 2, 3, and then configuration 3 is split in 2 plots because they are being fed in series. So that's why we have the 2 different graphs here. But anyway, the key message here is, again, we have concentrations decreasing several orders of magnitude along each treatment train. So this is the neutralization tank, the one that is receiving the influent. Then as this water goes through the upflow gravel beds and the planted marshes, and then finally goes through the effluent point in the last planted marsh, in this case, the concentrations have already decreased at least 1 or 2 orders of magnitude. So we are achieving contaminant removals of almost 90% and above, with a few exceptions here and there. But in general, the performance is really, really good. And then here is like the results summarized for treatment train B, which is it doesn't have pH adjusted, but similarly, again, we don't see pH being a key variable here, and we see contaminant concentrations decreasing several orders of magnitude. So where are we in terms of next steps? Let me see what happened here. Okay. So as I mentioned earlier, the pilot test operation, it's going to continue for 6 months more. So it's a total operation time of 12 months, and it will end in June next year. Now with the data we have collected so far, we are going to conduct detailed stoichiometric and mass balance analysis to understand if all the chloride, nitrite that are being generated or that are present in the system could be linked stoichiometrically to the mineralization processes of these contaminants, which is what we are simulating, what we expect is happening here. But again, we want to do sort of a mass balance to close in that loop and make sure that's the case and it's not other processes taking care of these contaminants. We also have DNA samples that are being collected so we can over time, and we want to understand how these microbial populations are changing over time and how well that data matches with the contaminant concentration data we are obtaining. We also have compound-specific isotope analysis, which is a very nice additional tool that will help us confirm if the right degradation pathways are happening here. We are going to be taking advantage of some of the infrastructure we have in place right now to do a bioventing pilot. So what happens if we don't only oxygenate the aquifer, but what if we provide some oxygen to the unsaturated zone, just to the soils on top? Like, could we also drive degradation processes in that unsaturated zone? So we'll be looking into that in the next few months. And then we are also going to start operation of the groundwater recirculation system. So far, everything we have done has been focused in biosparging and the wetland pilot test alone. We haven't initiated the groundwater recirculation component for the biosparging system yet. So here is a picture of the groundwater recirculation system that will be installing in the next couple of months. So you can see 2 tanks. One tank will be the equalization tank that will receive the effluent. Then that effluent will be pumped to another tank where will be oxygenating that water. So not only we are adding oxygen into those sparging wells in the subsurface, we are also going to be oxygenating that water that we are extracting and providing additional oxygen to the subsurface, but we also expect to be using concrete beds to help adjust the pH in that effluent before we inject it again to the aquifer and create a closed loop that can help us maintain pH conditions. So that's what we are hoping to do in the next few months. And well, with that, I think I'll just close the presentation. We have obtained very promising results so far. We hope to be looking into the details of the exact processes that are driving this contaminant concentration decrease and confirm that is indeed biodegradation. However, none of this would have been possible without team collaboration. So I just found this really nice quote. I really like, honestly, I didn't even know the author, but I found the quote and I love it. But the key here is that no one can whistle a symphony. It takes a whole orchestra to play it. So we can be great individuals. We all have like a great value to bring, but it doesn't become a masterpiece until you have an orchestra like playing it together. So each team member is essential. Each team member has expertise, has like contributions to drive this into a successful project. So I would say that has been one of the key components for the success that we have obtained so far with this pilot test. And with that, I will take any questions.
Okay, thank you, Paola. Just a sec. Well, would you like to thank Research Paola for the excellent presentation. I'm sure it was of great value for our viewers and fellows. And now, following our procedure, we invite chairs to make questions and give comments about the lecture. Please, who wants to start? Please open the microphone.
Erin's microphone is already open, so go ahead.
Okay. Paola, thank you so much. That was a great presentation, and I just really appreciate you showing this work. We're looking at two very different pilots, the ex-situ with the wetlands and the in-situ with the sparging. And they have a lot of similarities, but how do they address different problems? How might where would you use wetlands in the full scale, and where might you use sparging? And, if you were going to apply those.
Yeah, that's sorry, go ahead.
If that makes sense, yeah.
Yeah, that's an excellent question, Erin. And actually, they are two different pilots by nature. So the nice thing about the biosparging pilot is that we don't have to do any pumping or have all this above ground infrastructure to treat the effluent. Like, we can just simply work in situ under in situ conditions just by providing air and driving those biodegradation processes. And that works for areas that are easy to access, where we can easily deploy these biosparging wells. It also works even in the groundwater recirculation component, even works in areas that are not so easy to access. And then we can just have wells in the upgradient and downgradient end of that source area. However, for the wetland to work at a full scale, we need like a large area for implementing it. And that's not something that we have accessible in all parts of the site. It will also have like a high energy cost when we are trying to pump that water from the aquifer to then treat it through these natural treatment systems. But it also has the advantage of, well, right now we have an effluent that is being generated at the site from this hydraulic barrier pumping that is taking place. The site has boundary, wells at the boundary that extract water to prevent the migration of that contaminated groundwater offsite. So they are just taking water from the aquifer and it's being discharged to a wastewater treatment facility. Well, can we treat that? So, that's like a nice alternative that the wetland system can give us. And, the space can be like a limitation at some point. But right now we have all this northern area of the site, which is green areas. And even some of those areas are already like natural marshes. They are like flooded areas where we already have some of those natural conditions, so maybe we can take advantage of those. But again, the wetlands won't be the answer for the entire property. So we have different needs in different areas, and we need to customize the solution for each one of those so we can achieve site cleanup as a whole.
Good answer. I like that. And I think my second one, and this might be a little bit evil. So we've talked about the lab studies and the pilots and full scale, and it's a process, each step. Looking back, is there anything you'd have done differently? Is there a study we should have started earlier? Something we should have thought about earlier to test?
Yeah, that's a tricky one. I want to know too. No, that's fine. I think, I don't know, personally, I love every step of the way. It was like a very robust team, and I think we could have skipped some things, like, for example, chlorobenzenes. We know they are mostly degradable. Chloroanilines have also been reported to be degradable in the literature. However, we wanted to know if they were there. So I still see a lot of value in the microcosm studies that were performed. There were also like multiple stages of design. So I think these are relatively simple concepts that are rather easy to implement, but because it was the first time that we did it like at this site, and it was like a very large, complex team, complex mixture of contaminants too, we wanted to be very careful in every step of the process. But I think in the future for other areas, it will be very easy to make that jump from, well, this work here, what, can we easily move it here without any long stages of like design or anything like that. So yeah, I think like now we can streamline the process for implementation in other areas, the key answers we are getting after this comprehensive step-by-step process that we follow.
Great. Sávia, your turn.
Thank you. This is amazing. It's such an amazing project. Yeah, as you said, it's a great team. I see this is the way the nature works, right? We have geochemistry, biology, chemistry, engineering, geology, all together in to solve one project, so to solve that problem. So it's amazing to see this project. Paola, a year ago, Erin was here in Recife, and she talked to us how cooperating with universities and consultant companies could boost solutions and improve human resources formation and sharing knowledge and vision. So I would like to hear your opinion on that and your vision about this project, the way it's conducted, and the way it puts people together.
Yeah, I love that question. Thank you for that, Sávia. Yeah, I think it has been key here, the nature of like nature and extent of collaboration we have had. Like, you know, we have like the engineers and the geologists that do not always like they are not always heavily involved with academia, so like professors doing research and all like the newest developments, how to make things in a more innovative way. So we had that very interesting interaction where we had, you know, researchers from different universities in the world, top researchers honestly, sharing with like engineers that have been working in pilot testing or like full-scale implementation of this type of technologies, and then finding the innovative aspects of each one's field to implement this pilot test successfully. So again, we had a very exotic mixture of contaminants that had not been studied before. We got that from all the comprehensive research that was conducted with universities, but that wasn't enough. Like we need to take that and apply it into the field. So we needed that bridge between academia and consulting to make that happen at a field scale. So what was successful in the lab could be successful at a field scale. So that was great. On the other side, we had like the client like being a former industrial facility that it's facing its own challenges, also having to demolish and remove some of the former production units. And then how do we integrate that with the remediation schedule? Because we cannot just do whatever we want. We also need to take into account all these other business drivers that are ongoing. So we needed to find like the right point to integrate everything. And I think this was great. And again, not only the different fields from where we work, consulting, academy, industry, but also each profession, as you said, geologists, microbiologists, engineers, each one brings different value to the table. This is not a unidimensional problem. It has many dimensions, many complexities, and then each one can contribute to figure out each one of those complexities so we like achieve the best results possible. So that was great. We have like a very diverse team. Also culturally, we had people from Brazil, we had people from Canada, the United States, people from Europe. Like, you know, in some meetings, like, you know, there were like 4 different languages or people that, you know, would have 4 different like native languages, and sometimes communication would be a challenge, right? Yet, you know, we find the right way to make it work, and here we are. So
Yeah, this is awesome. I see how my students have improved since they started in this project, and professionally and personally as well. So they are challenged every day, and this is awesome. I have another question. It's about the pH adjustment that you mentioned, and how to adjust the pH in a way to guarantee a good distribution. Have you thought about that?
Yeah, so the pH adjustment has been a tricky aspect because, well, ideally, at least in other areas or other countries, like the United States, is very easy to get approval to, add certain reagents that can be a help or can help buffer pH. However, in Brazil, that's not necessarily the case. So we have to get approval from IBAMA to inject any type of buffering reagent. And actually, there are no buffering reagents approved right now by IBAMA. So we originally were considering using dipotassium phosphate or maybe even low doses of sodium hydroxide, but we cannot use any of that because it's not approved by IBAMA. So instead, what we have resourced to is using crushed concrete, and that's where the sustainability metrics come in place. So we don't have approval to use those other reagents that give us some comfort because we can easily regulate, we can easily dose. Doing pH adjustment with concrete beds is more tricky because we cannot easily dose concrete. We have a concrete bed of whatever many tons and we need to add more, take more. It's not as easy as a dosing pump. So that has been challenging. However, it goes aligned with the sustainability metric where we are taking advantage of resources that are already on site to drive these changes, these processes that we want. So in the subsurface, it's tricky. Again, for pH adjustment, we are doing it all above ground. So for the biosparging component, we are extracting that groundwater, pumping it to a tank, and then that tank will have a concrete bed. And after certain residence time, that that water is pumped again and injected back into the aquifer. And then we expect that injection, and we are going to be assessing all of that. What's the radius of influence of that injection? After I have adjusted the pH in this water and I'm injecting it, now it comes to a question of, well, how well is that water spreading, that pH buffering throughout the subsurface? So we don't know the answer right now because that's exactly what we are going to start doing. But so far, at least based on the good level of oxygen distribution we have achieved, we expect that we can easily circulate that pH adjusted water throughout the aquifer, and that won't be an issue, but we'll see in the next few months. So I don't know if that answered the question.
Thank you so much, Paola. Yeah, perfectly.
Okay.
Alan?
Anyone have more questions? No? Well, since we no longer have questions from chairs, let's move to questions from Facebook and YouTube. We have some questions here. Paola, do you have time for more questions? Maybe 5? Yeah. The first question is from Professor Bruna Fernandes from the University of Pernambuco. First, she talked. Dear Ms. Paola Quintero, thank you for this nice and very interesting presentation. Could you tell us which is the biggest challenge to control and remediate this contaminated site?
Okay.
That's the first question.
The biggest challenge to control and remediate this site. I think the biggest challenge we have been dealing with here is the nature of the mixture of contaminants we are dealing with. Again, some of these contaminants are commonly found in the remediation industry, but the exact mixture and some of the individual components are not very common themselves. So you cannot easily resource to doing a literature review for this mixture and then find answers from experience that others have acquired for this type of mixtures. Instead, we didn't know how that was going to perform, so we had to do a lot of the treatability studies. That's why we are investing a lot of time in pilot tests, because again, that background knowledge for this complex mixture, and not only the complex mixture, but also the levels of contaminants, contaminant concentrations we are dealing with, is very high in certain areas. So one of our questions will be, well, this pilot test work in this area, which is contaminated, but is not the hottest area at the site. We have areas at the site that have like even higher contaminant concentrations. Can microorganisms perform for this type of impacted areas as well? Can they also degrade those highly impacted areas? So, that has been a challenge, like the combination of contaminants we have, along with presence of NAPL and high contaminant concentration, both in soil and groundwater.
Well, there is a second question related to this question from Professor Bruna. What are the parameters and strategies to define which process to adopt in remediation a contaminated site?
Okay, so what are the parameters to define which processes will be adopted in the remediation? Okay, so for this remediation process, we have remediation goals, right? We need to know what is an endpoint, how good or how clean is clean. What's that contaminant concentration goal that we want to achieve, at which we think it's safe if anybody was going to be exposed to that contaminated media, that there wasn't going to be any risk. So we have these concentration goals, or these remediation goals. The basis for defining which remedy will be implemented will be based on effectiveness, which is largely determined by how well does that technology removes contaminants to achieve those concentration goals that you have established based on risk or on exposure. So that's one key component, effectiveness. Then we also have, of course, cost, like the economics of the process. We can have a great remedy, but if it is crazy expensive, it's not going to be realistic to implement. Like, the business cannot afford that. So we need to find a balance between effectiveness and cost. We also are taking into account sustainability aspects. So we are also weighing in, well, in terms of sustainability, which remedy performs better than the other. So that's also a driver for implementation. And I think I'm missing another one. Erin, can you think of another one?
Sustainability, meeting goals.
Yeah. And then the cost, and then time, exactly. The time for the performance, like, we have, and time goes along with cost, and the more time it takes, the most it will cost. So yeah, those are like the four main parameters. Well, and also how easy it is to implement, because there are many technologies out there, but unfortunately not all of them are easy to find in Brazil. So not necessarily the equipment or the experience, people or teams or technologies, they are not always available in country. So it's very hard to import these technologies in country. It's hard from a logistical point of view. Economically, it's expensive. So easy to implement that remedy, it's also key. So actually, I would say it's like 5 aspects. Effectiveness, which goes along with how well can we achieve those remediation goals. Economic aspect, cost, time for implementation, sustainability, and also ease for implementation. How easy can we implement this under our conditions and our reality in this area?
Well, we have more questions from Felipe Filgueiras. It's a grad student from Professor Sávia. What was the difference between the degradation efficiency with and without recirculation in biosparging?
Yeah, that's a great question. Thank you. So actually, we are seeing already very good results with biosparging alone. So just based on biosparging alone, we already have really good dissolved oxygen concentrations in the aquifer, and we have seen contaminant concentrations decrease significantly, orders of magnitude, as you saw in those plots. However, like, that biosparging system only has a radius of influence. Based on this amount of air that I'm injecting, I can only get this far. If I am recirculating groundwater, and that is groundwater that I'm extracting, oxygenating, and then injecting again, I will expand that radius of influence. So if before the footprint for dissolved oxygen was, say, I'm saying this randomly, I don't know, 100 cubic meters, 100 square meters. Now, by adding another source of oxygen to the aquifer, you will further expand that zone of influence for that oxygen that you're supplying. So if you could only remediate this smaller of an area, now that you're doing groundwater recirculation, you're helping expand that radius of influence of the remedy. And then in addition to that, the main reason why we are doing this is so we can provide pH adjustment to the aquifer, because right now the biosparging alone doesn't have that component. However, when we do the groundwater recirculation, we'll pump this water into a concrete bed that will alkalize the water, and then we'll inject it again. So that will help us provide alkalinity to the aquifer to help that drive that pH up, because right now it's going very low, and if it gets very low, it may shut down any biodegradation. So we have seen that pH is a key variable, at least in the lab, for biodegradation. So we want to make sure that pH is high enough that microorganisms are happy, so they continue to degrade these contaminants. And then lastly, I'm talking too much. Lastly, the groundwater recirculation, it's also an option for those areas that have buildings in place. So if I have a unit here, it won't be easy to put a biosparging well in the middle of it, because I have this gigantic building here. I cannot go and drill the sparging wells that I need. Instead, I have access on the road that is upgrading or downgrading, at the boundaries of the unit. So if I can extract and pump and inject again and recirculate, oxygenating that water in the above ground portion, then I am finding an alternative to those areas where I cannot install anything in place, but I need to work in the borders. So this is a nice option for that too.
Well, there is another question from Felipe related to this one. Is there any compound that was not biodegraded before recirculation, and after it become biodegradable?
No, I think so we haven't started with recirculation so far. We have only done biosparging, but all of the contaminants that we have at this site with biosparging alone have been degraded. Not in all the wells, as I mentioned. In some wells, certain contaminant concentrations are going up, but in other wells, that same contaminant concentration is going down. So in general, that contaminant can be biodegraded under in-situ conditions, but in some wells, there are some other things that are going on and that we are trying to understand where that contaminant concentration it's increasing. But in general, and the groundwater research. Did you guys lose me there?
Oh, yeah. It was
Hello.
a little cut off from the internet.
Yeah, but she's back.
Mm-hmm.
Oh, okay.
Just a little.
Okay, sorry. So did you hear that?
Yes.
I think so.
Okay.
There are more questions. Mateus Paraíso, are there any kind of microorganisms present in all CI degrading cultures, or are the cultures more specific?
Yeah, and actually, Erin, if you can provide any help here, you're welcome. You're the microbiologist. But yeah, I think we have done a lot of DNA extraction and sequencing work to identify each species that is degrading these contaminants. So along with all the work that the universities did, they have identified the species that are mostly taking care of these contaminants at the site. They have isolated them, and there is actually also some talk about developing specific DNA probes to identify them with additional sequencing work. But I don't know, Erin, if you have any names on the top of your head with regards to which species specifically. I remember Pandorea but like that's taking care of chlorobenzenes. Anyway, I'm not good with these microorganisms names, but I think we have identified some.
And I'm going to sound really old because they're all Pseudomonas or Burkholderia, which we don't use those names anymore. I have old names for them, but I think it does seem that there's an organism that there are different organisms for each COI. It's not one organism that does all of them, and that's been a really complex story. And Sophia and Natana have really been digging into that. It takes a village to break down a bunch of contaminants.
Yeah, that's a great point, Erin. Yeah, thanks. So yeah, the answer is we have identified those microorganisms at a species level, and we'll be doing additional work on that.
Right. It's a developing story, definitely.
Exactly.
We have more questions. Professor Vanderlei Leite from Federal University of Pernambuco. What were the criteria to choose plant species?
Yeah, for the wetland pilot. So for that, like the main driver was
wetland pilot test.
Yeah, can you guys hear me? I think I'm having some issues with the internet. Okay.
We can hear you.
Okay.
Yeah.
So
we have feedback.
Okay, good. So for that, we wanted to choose species that were native to the area. So we are working, for example, with Junquinho, which is like a species that is like it's easy to find in Bahia. We are actually working with Universidade Federal da Bahia, and we have like a researcher, Gilson Carvalho, who has been helping us through that process and also like pick the plants and evaluate how they are performing over time, how healthy they are. But mostly the key driver is we wanted species that were used to the weather conditions and the general weather in Bahia, so they are all species that are easy to find in the Bahia area. So that was the main component there.
Okay, we have another question from Professor. Does the plant can assimilate contaminants, or it only provides a source of oxygen for aerobic microbes to carry on the process?
Yeah, that's an excellent question too. So for that, I don't think we have the answer right now. That's like part of the questions that we hope to be answering here. If there is any actual like contaminant uptake and storage in the plants, or if some of those contaminants can be metabolized to a certain point by the plants, what exactly can the plants do for us? We know of many benefits of these plants, like in the rhizosphere area, like the variety of microbial populations that can grow in them and can enhance biodegradation in that area. But with regards to the plant itself and how like it can uptake or assimilate those contaminants, that's something that we are looking at. Like University of Bahia indeed will be collecting plant tissue samples at the end of the pilot and be analyzing for the contaminants of interest to understand if they are being accumulated by these plants, or if we can detect them in these plants. And I don't know, Erin, if you would like to add anything there, like any insight you may have on that aspect.
I think you covered it, whether the plants accumulate or produce the right environment to enhance degradation. I think those were the two keys. And trying to think if there was any other aspect. I think too, we want to understand if we don't want to create a bigger problem with the plants by attracting, if they accumulate it and some wildlife comes to eat the plant, maybe that's not good. And it shouldn't happen with these compounds, but you never know, right?
Yeah.
No, those are the things we want to look at. But the science on the rhizosphere as a very important area for biodegradation is a really hot and developing area right now, and this should be an interesting place for microbiology and plant biology to work together.
Agreed. Yeah. Thank you, Erin.
We have one last question from social media from Professor Bruna Fernandes again. Why to adopt biosparging instead of anaerobic bioremediation? For example, adding electron donor by biostimulation. Is it more cost effective?
Yeah, that's a great question too. And actually that was one of the questions that we intended to answer with the microcosm studies that were performed by all these universities. So the answer that we got is like with the anaerobic processes, it was more of a biotransformation process. So we had this parent compound, but this parent compound was transformed into this other compound, which is not necessarily a better endpoint. So we had dichloroanilines being reduced to chloroanilines. Chloroanilines are still toxic. They are still not good for the environment. So we wanted to make sure that if we go the other path, for example, like contaminant oxidation or mineralization, these parent compounds are simply oxidized to carbon dioxide and water. There is not a better endpoint than that, actually. And we know that some processes of interest in the remediation industry are focused on anaerobic processes, but like, you know, chlorinated ethanes, and we have the vinyl chloride. Vinyl chloride sometimes becomes an issue, so that's of a concern. We didn't want to have like a similar situation. But in this case, this side, it wasn't also difficult to add air. So we had like a rather porous matrix where we could easily sparge air and distribute it in the formation. So that's like an easier and better answer rather than having these intermediate compounds being generated. And some of them are endpoints. Some of them are generated, and you know, that's like the most reduced form of that contaminant. It doesn't get further reduced and is still a contaminant with certain toxicity that you cannot just leave there. So that's the reason why we went with the aerobic path rather than the anaerobic or biostimulation. Erin, I don't know if you want to add anything to that as well.
Fast. Aerobic processes are fast. And I love anaerobic processes, but the aerobes are really fast.
Yeah, that's great. Great point too.
Your answer about the engineering aspect is a really important one. This is a site where we could do this, and you know, the engineering parts of this are as important as the technical understanding of the fate of these compounds.
Agreed. Thank you, Erin.
Are there any more questions from chairs? No?
No, I don't.
No, I'm really happy and thankful.
I have the right to do a simple question.
Sure.
Of course you have. You're big. I see. I can see. You don't have a wall in your back.
Just out of curiosity, could you, Paola, talk a little bit more about the vapor extraction well?
The vapor extraction wells?
Is this a system? What's the fate of this vapor?
Yeah.
And separate zone?
So we are injecting air. We are not injecting pure oxygen. So because we are injecting air, we know that is 21% oxygen and the rest is nitrogen and other gases that won't be degraded. So that means that while the oxygen gets consumed in the subsurface, all those other gases will stay in there. They won't go anywhere. Like they will have to vent somewhere because, you know, they cannot accumulate in the subsurface indefinitely. So we need to provide a path for those vapors to escape in a controlled way. So we are injecting all this air. Some of it is being consumed, only the oxygen is being consumed. The rest needs to go somewhere. And we don't want it to go anywhere, you know, like just go to a well that is, I don't know, like 500 meters in one direction, and then somebody goes and sample it and push, all this air comes and splashes and whatever. So we don't want that. We want to provide control means for that air to come out of the subsurface, be captured and treated before it's emitted to the atmosphere. So that's what the solid vapor extraction system and the passive venting system allowed us to do. The passive venting system in the saturated zone and the solid vapor extraction system in the unsaturated zone. So they both are capturing vapors, taking them to activated carbon, and then those treated emissions are released.
Thank you. Thank you. Thank you so much, Paul. Congratulations. It's an amazing project. I'm very happy to see a group, a team of our university participate of this project. It's very.
Okay.
Nice to meet you, Erin.
Nice to meet you.
Thank you, Sávia, to do this link with Erin and the invitation of Paola to participate. A great presentation.
Thank you.
Thank you so much.
Okay.